Hello everybody, we're so glad to be part of BlackHat and present our research hunting rootkits with eBPF, in which we analyze the most common rootkits in Linux and found common behavioral patterns between most of them. Rootkits has always been a major part of the APT toolset, but nowadays we see more and more emerging attacks that make use of this advanced malware. Tag along to a journey in which we dive deep into the workings of rootkits and how to detect them. Along the way, we'll also explore the exciting new technology of eBPF and how to use it, and we'll present our open source project, Tracee. But first, a little bit about ourselves. So I'm Asaf Eitani, a security researcher at Team Nautilus, Aqua Security Research Team. Aqua is a cloud-native security company, which obviously takes great interest in Linux because most of the cloud runs on Linux. In my past, I've done mostly forensics and incident response, and nowadays I'm more focused on low-level Linux research and eBPF development.
I'm Alon Zivony, also a researcher in Team Nautilus of Aqua Security. I have experience in embedded R&D and also in vulnerability research. Currently, I focus mainly in eBPF and also low-level Linux development and in kernel vulnerability research.
So, what will we have today? First of all, we'll take a quick scoping around the kernel, see what it is. Next, we'll go through the tracing methods available to us in Linux operation systems, and we'll focus more on eBPF and how it works. Then we'll see what rootkits are, and we'll present the results of our research, which is the rootkit attack flow and how to detect it. Finally, we'll see what's next for our open source project named Tracee. Okay, so I'm sure most of you already know what the kernel is, but we'll do a quick scoping. So every modern computer is divided into the user space and kernel space. User space is where all the user space application resides, such as text editors, email programs, and internet browsers like Chrome or Internet Explorer. May he rest in peace. We will not miss him. The kernel is the operation system and all the systems that supports it, such as privilege management, file management, and memory management. Syscall are the intermediate between the two and sort of like an API between the user space and the kernel. So when we're talking about detection, we have to talk about tracing. Tracing is the act of monitoring the action on a computer. When we're picking tracing methods, we have to pick the features that we want it to have. So first of all, we want it to be as efficient as possible. We also want it to be as stealthy and have a strong security boundary so attackers won't be able to disrupt it as much. We want it also to have a full system visibility so it will see as much as it can. And finally, we want it to be safe for our application to run. So in front of you is a table of the tracing methods available in Linux operation system. The first two, ptrace and library injection, are user space tracing methods. As you can see, they don't quite fit our needs because they lack some of the features that we want to have. Either they are not as efficient or doesn't have a strong security boundary. In any way, both of which can't access the kernel, so they can't provide us with the full system visibility. Kernel modules, on the other hand, were the go-to solution for many years for tracing methods, but as you can see, they're not quite safe. An error or a bug in kernel module can lead to a system crash or even a vulnerability to be exploited by the attacker later. eBPF, on the other hand, has all the features that we want because it's sort of like a kernel module, but it's running in a VM sandbox inside the kernel. eBPF also has a mechanism for verifying your actions so you don't do stuff that can cause a crash like null pointer reference. eBPF has also access to features in the kernel named probes to be able to allow us to hook on certain kernel functions. So, we've mentioned hooking, but what is hooking? Hooking is the act of attaching oneself between two functions in the execution flow, by that gaining the execution context. That means that we can see what the calling function used as argument to the call function. In eBPF, we have access to probes. There are many types of probes, but we will be focused on three today: K-probes, trace points, and U-probes. K-probes are dynamic kernel hooks within the kernel, meaning that you can place a hook on almost any kernel function and be able to monitor it. We've written LSM hooks and we'll talk about it in a second, but generally, LSM hooks are places in the kernel that are meant to be hooked by K-probes and has security meaning to it. Trace points, on the other hand, are static kernel hooking, meaning that they are placed in static location that can be used by us. U-probes are very much like K-probes, but they're only in the user space, not the kernel. We've mentioned LSM hooks before, but why do we need it? LSM hooks helps us avoid problems like talk-to. Talk-to, or time of check to time of use, is a race condition vulnerability which can be used against us. We'll explain what talk-to is through an example of process creation. Let's say we have our user space malware which want to invoke a new process creation. The first step is to write the desired path into its memory. The next step is to provide a pointer to that path to the execve syscall, which in turn reads that path and writes it to a file struct in the kernel. The problem is our syscall trace points gets also the same user space pointer. The malware will then spawn a new thread and overwrite the original value for something legitimate like bin ls. Now our syscall trace point will read that value and store it for monitoring, indicating a wrong process creation. Execution is then going deeper and deeper into the kernel, into security BPRM check and sketch process exec, both of which read the value from the file struct in the kernel, as we mentioned before. As you can see, we have on both of these functions LSM hooks or trace points, which allow us to get the value from the file struct that will be executed. So we've seen that LSM hooks can help us avoid talk-to, but it has some extra advantages. The main one being path resolution. Relative path and symbolic links are already resolved in the kernel, so we are getting the absolute path of the binary to be executed. So we've seen what is eBPF and why it's so great, and let's talk about our open source project. Tracee makes use of these eBPF features to increase observability into the kernel. It also has some neat features like artifact capturing, meaning that we can capture files that are executed, memory dumps, or even network captures. It also has behavioral detection based on our engine. You can see the code of Tracee and support it on GitHub. Okay, so before we proceed into Rootkits, we want to show you a quick video from our favorite movie, Mission Impossible, to help describe the problem that we want to solve. So, as you've seen, our legacy antivirus thinks that everything is clear, but in reality, we have the rootkit that hides our malware. So what is a rootkit? A rootkit is a malware which purpose is to hide itself and other malwares or artifacts in the system. It's doing that by hiding artifacts like processes, files, network connections, kernel modules, and even itself. That obviously makes it really hard to detect, and most of the time you won't even know it's there. In this presentation, we'll be focused more on kernel rootkits rather than user space rootkits, although they exist. So, after 6 months of intense research, we are proud to present to you our kernel rootkit attack flow. We will take you step by step into each phase of the rootkit attack flow. First of all, a kernel module must be loaded, after which the kernel module wants to hide itself to avoid detection. It proceeds into placing hooks upon the system to be able to hide other artifacts like processes and files, and it establishes a communication channel to be able to get commands from its operators, either to a C2 channel or a user space malware which acts as the intermediate between the two. Finally, it gets a command to execute and executes it. Loading the kernel module can be done with two syscalls, finit module and init module. They both operate pretty much the same, but the main difference is that finit module loads the kernel module from a file, as init module loads a module from a memory buffer. As you can see by the diagram, both of which call doInit module to actually load the kernel module. Tracee uses this kernel function to detect that a kernel module has been loaded. It's important to state that once a kernel module was loaded, Tracee and it both operate in the same space and they can both disrupt each other. In the following demo, we will see an example of how Tracee can be used both to detect and capture kernel module loading. We'll see how we dump a kernel module into memfd, which is a memory-backed directory, so it's not really written to disk, and now we load it. So above we have our Tracee command line with all the relevant events, and magic write, which indicates our file creation, and the -c meaning capture. We have our nginx running in the background, a vulnerable nginx, and we execute our exploit. You can see the 3 events were invoked. The magic write, which indicates that the file was being dropped, and 2 events that indicate a kernel module being loaded. As you can see below, we have our kernel module being captured to disk for later investigation. So now that we've seen how we can load the kernel module, how can we hide the kernel module? First of all, we need to understand how kernel modules are stored in the memory. Kernel modules are stored in the memory in a linked list. So each kernel module is connected to the next and previous one with pointers, next and previous. When a program wants to enumerate all the loaded kernel modules, it simply goes to the first one and continues with the next pointer until it reaches the beginning. A kernel rootkit can detach itself from this linked list by modifying the next and previous pointers. By doing so, it's basically invisible. So when a program iterates over the list, it will simply skip over our rootkit.
So we've seen how rootkits get loaded and afterwards how they hide themselves. But how do they implement their main functionality to hide artifacts across the system? To do so, they place hooks in multiple places across the system. We go over 2 main techniques used by syscalls: syscall table hooking and file operations hooking. We start with the syscall table hooking. Syscalls are the interface between the user mode and the kernel mode. Whenever a program in the user mode needs something from the kernel, like doing some operation or maybe get some information from the kernel, it will invoke a syscall. Then the kernel will find the right handler for the syscall inside the syscall table entries and call this handler. The handler will do the operation and return the response to the user. For example, we have the ls command in user mode that needs to list all the entries inside the directory. To do so, it invokes the getTheEnds syscall. The kernel will find the right handler for the getTheEnds syscall inside the syscall table and call this handler to do the operation. In turn, it will return all the entries inside the directory. In this case, we see a malware file inside the directory and return to the user. The ls command will print this list of entries. So, how a rootkit can hide the malware file from the user? To do so, we'll place a hook on the getTheEnds handler. You will do it by overwriting the entry inside the syscall table of the getTheEnds syscall. This way, when the ls command will call the syscall, the entry will be found of the getTheEnds inside the syscall table, and the hooked syscall will be called. This hooked syscall will most probably call the right getTheEnds handler and get the right response in return, and then modify the response before getting it back to the user. This way, it can remove all entries that you want from the directory, in this case, the malware file. So it seems like the directory is completely empty, even though we know that there is a malware file inside there. So how can we find this syscall table hooking? All entries inside the syscall tables points to the right handlers. All the handlers are part of the original kernel code, so they reside inside the text section of the kernel, which is bounded by the stext and etext symbols. However, if an attacker puts a hook on the syscall table, it will override the entry and put a pointer to its own implementation. This implementation will be part of its kernel rootkit. So this function will be inside the kernel module allocation section. It means that if we iterate over all the syscall table entries, we can find for each entry if it's hooked or not hooked by the place that the implementation resides in. For example, we have the diamorphine rootkit. Diamorphine is very, very popular open source rootkit. One of its functionalities is to hide processes from listing utilities like PS. These utilities most of the time iterate over the proc file system. So by removing entry of a directory inside the proc file system, we can remove a process from the listing. In the left side of the slide, we can see the implementation of diamorphine. At first, diamorphine gets the address of the syscall table. Then it saves the original handlers of the syscalls you want to hook. In this case, we have the kill, get the ends, and get the x64. Then it will overwrite the entries of the syscalls with its own malicious hooked functions. In the following demo, we'll see how Tracee is able to catch syscall table hooking as we saw earlier in the implementation. So at first, we run Tracee with the hook syscalls event. This event will be triggered whenever Tracee runs or whenever a new kernel module is loaded into the memory. So at first, we can see that there are no hook syscalls at all at the system. Then we will load diamorphine, and we see 3 hook syscalls, kill, get the ends, and get the x64. All the 3 syscalls we saw before. We can see that they are part of a hidden module because diamorphine is hidden. So we'll unhide it using the kill command. Then we start Tracee again, and we see that the 3 syscalls are part of the diamorphine kernel module. So we saw how you can hook syscall table, but syscall table hooking is a very broad way to do hookings, and it only affects the interface between the user mode and the kernel mode. So if you want to use more sophisticated and deeper implementation of hookings, you can use something like file operations hooking. In Linux, everything is a file, and each file needs to implement some file operations like read or write, which are very basic. It can also implement many other file operations that are more complicated. These file operations all reside in a struct named file operations that have all pointers to all the file operations that are available for a file. These file operations are implemented for each file type, and we have many global file operation structs inside the kernel. Whenever we use binls, for example, the getTheEnds64 will be called, and this syscall implementation will use the iterate or iterate shared file operations of the directory entry, and we'll call the implementation from there. Then we'll get the response and give it back to the user. So how can a rootkit hook these functions? To do so, it can override addresses of the file operations inside the file operations struct. This way, whenever the file operations are called, the hooked function will be called instead and can modify the response. For example, with the getTheEnds syscall, it can modify the response to remove the entries that in turn will return to the binls and not be printed. In the following demo, we'll see how the phide kernel module or rootkit hide a process and how Tracee is able to find this file operation hooking he uses. The file operations hooking event will be triggered whenever the proc file system is referenced. So at start we run ps, and we can see that the hide process listed inside the ps command. And we can see there are no file operations hooked at all. After we load the phide kernel module, and we can see that the hide process is hidden from the user. However, we can see in Tracee that there are 2 pointers hooked inside the kernel. The entire file operations struct pointer points to inside the phide kernel module or rootkit. In this implementation of this kernel module, the iterate shared pointer points to also phide kernel module instead of the write handler, which is the hooked implementation of the phide kernel module. After the rootkit has deployed its hooks and compromised the system, the attacker needs a way to communicate with the rootkit, to dynamically hide artifacts, or maybe even do more complex operations, like escalate privileges for a session, or execute command from afar in high privileges. To do so, the rootkit establishes communication channels. It might be network communication with a C2, and maybe create a new device or file to communicate with using read and writes. It even can be a syscall table hooking, like we saw earlier. It's really a game of creativity, and there are many ways to implement it.
Okay, so we've seen how kernel rootkits operate, how they're being loaded, how they remain hidden, and how they place hooks upon the systems like syscall table hooking and file operation hooking to hide other artifacts. We've also seen that there are many ways to create a communication channel between the operators and the rootkits. Now we're getting to the final stage of command execution. We'll give an example of a process creation to demonstrate how they can do it. Process creation as command execution is the holy grail of attackers, which allows them to do as they please in the compromised host. So, as we mentioned before, process creation is invoked by the execve syscall, which in turn calls security BPRM check and sketch process exec. But there's another way to invoke new process creation in the user space by using the call user mode helper kernel function. That's interesting because most security measures and tracing methods will hook upon the execve syscall to detect new process execution. But using the call user mode helper will allow us to bypass all those security measure and tracing methods. As you can see, attaching ourselves into lower kernel LSM hooks and trace points allow us to identify that a process was created. In the following demo, we will see an example of how Tracee can both detect process creation from the user space and the kernel space. As you can see, we have our Tracee CMD line, which contains the relevant events. As we are running Tracee and we run our user space process, we can see 3 events were invoked. We will then load our kernel module, which will invoke a new process creation from the kernel. As you can see in the 2 highlighted parts, the first one being the user space process creation. As you can see, we have the event execve, then security BPRM check, and sketch process exec. You can also notice that in the bottom left corner, we have the invoked from kernel flag, which is 0. In the bottom one, we see the call user mode helper, and then the security BPRM check and sketch process exec. And as you can see, our flag for invoking from the kernel is 1. So, what did we have? First of all, we've seen an example of how a kernel module can be loaded, detected, and captured for later investigation. Then we've seen an example of how a kernel module might hide itself. We've seen 2 examples of how hooks can be placed using syscall table hooking and file operation hooking. We then discussed on the possibilities of communication channels and how it's all really a work creativity. Then we've seen an example of command execution in the form of process creation from the kernel and how it might bypass other security measures. So, what's next for us in Tracee? We're planning to research about other hooking methods and to incorporate some U-probes to be able to detect user mode events as well as kernel space. We also want to incorporate LSM BPF enforcements to be able to block rather than only detect events in the kernel. As a parting note, I want to invite you all to be part of our community and contribute to our research and to Tracee as general. You can all access it in GitHub. Thanks for listening.